And N1 and N2 are the refractive indices of the material mediums we have chosen. Sin I being very small, we are going to approximate sin I to I. If the angle is increased more than critical angle, we can say that, okay, the phenomena of total internal reflection is going to take place in that particular medium. Since I is the exterior angle, then I can see that alpha plus beta will be equal to I. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with some optical instruments and their optical phenomena. So let's see what happens right now. So in the previous classes, we were discussing how the incident ray can actually undergo a certain phenomenon that is known as total internal reflection. That is, when a ray of light enters from a denser medium to a rarer medium, when it tries to enter into a rarer medium, instead of entering into the rarer medium, it is reflected back to the same medium itself, and that is known as total internal reflection. And we saw that there is certain conditions for that, there is certain needs to be met, and one of the particular needs was that it should be more than critical angle, and critical angle depends on the material or medium which we are using. So again, what does critical angle actually means? So if there is a material medium in which light is traveling from the denser medium to the rarer medium, right? And let's say this is the critical angle. Let's say this is the incident ray, and this is the critical angle. Let's mark it as C. And then we can say that the refracted ray is now making an angle of 90 degrees with the normal. Okay, this is the normal. And if the refracted ray is making an angle of 90 degrees with the normal, we can say that, okay, incident ray has approached critical angle. If the angle is increased more than critical angle, we can say that, okay, the phenomena of total internal reflection is going to take place in that particular medium. So let's say that, okay, this is medium 1, N1, and this is medium 2, N2, right? So N1 is the refractive index of material medium 1, and N2 is the refractive index of material medium 2 with respect to each other. Now again, we have already seen what all of this actually meant and how it happens. Everything was explained. Now we are going to look at what is the relation between what is critical angle and refractive index. So basically, we have a critical angle here which is indicated by C. Let's say this particular angle is theta C or just C. However you want to phrase it, it's completely fine. So what is the relation between this particular critical angle and the refractive index of the material medium? Because we just previously said that the critical angle of any incident ray or any material actually depends upon the refractive index of that particular material. Now we have to mathematically prove that, so that, yeah, we can definitely say, okay, refractive index of a material depends on the critical angle, or critical angle of any material depends on the refractive index of the said material. So how do we do that? It's very simple. We start from Snell's law. From Snell's law, we can say that, what is Snell's law? It's very simple. It's sin I by sin R is equal to N21, or simply N2 divided by N1, right? The ratio of sine of the angle of incidence to the sine of angle of refraction is equal to relative refractive index, which can also be written as N2 by N1, where N is the refractive index of the material, 1 and 2 is the respective material mediums. So again, in this particular case, I'm going to take that, okay, let the denser medium be water, and the rarer medium, let it be air. Why I am taking air as the rarer medium is because the refractive index of air is taken as 1. The refractive index of air is taken as 1, and with respect to that we can say that, okay, the other refractive indexes of certain other materials, in air it is 1. So as we move on to certain other like optically denser mediums, we can say that with respect to air, it is slightly more or less denser, like that we can say. So just for that case, air is taken as refractive index of air is 1. That is why I have taken air as the second or rarer medium in this particular case. Then I can actually rewrite this particular equation. That is, since C is the critical angle here, and N1 and N2 are the refractive indices of the material mediums we have chosen, and here it is water and air. So we do know that the refractive index of air is 1. So then this particular equation becomes, as I tends to be C, we can actually say that, okay, we can actually say that this particular equation now can be written as sine C divided by sine R is equal to N2 by N1. N2 by N1. So the first change I'm making is that instead of incident angle, I'm going to write critical angle C. You can either use theta C or C. I'm just using C. So I'm just using C as the critical angle. Then I can say that, okay, sine C by sine R is equal to N2 by N1. Now we are going to provide the angles or the values that is designated for each of these. For example, sine C, we don't know what is sine C. It depends on the material medium. So I'm just taking it as sine C. So I can say that, okay, sine C divided by, that is sine of the critical angle divided by sine of the refractive or refracted angle. Here, the refracted angle is nothing but 90 degrees. That is, this particular angle is 90 degrees, which means sine 90 is equal to 1. Right, sine 90 is nothing but 1. So we can say that sine C divided by 1 is equal to N2. N2 is the refractive index of the rarer medium, which is nothing but air in this particular case, and that is also taken as 1. So here it will be 1 divided by refractive index of the first material medium, which is again nothing but N1. So we can say that, okay, N1. So we have a final relation, that is N1 is equal to 1 by sine C. Or we can also say that sine C is equal to 1 by N1. If you know the critical angle, you can find out what is the refractive index of that particular material. If you know the critical angle, then you can find out the refractive index of the material. And if you know the refractive index, then you can actually find out what is the critical angle of that particular material medium. And that is the relation between sine C and refractive index of that particular medium. Or simply we can say that the relation between critical angle and refractive index is obtained in this particular fashion. First, we consider a denser and a rarer medium. We assume it to be water and air, and then we assumed a situation where the critical angle is achieved, and then using Snell's law we arrive at this particular result where N1 is equal to, or simply just N is equal to 1 by sine C. Generally we can say that N is equal to 1 by sine C. That is the most general definition, or just simply the general relation between critical angle and refractive index. So now we are going to look at a certain phenomena, that is what happens when light falls on a curved surface or simply a spherical surface. If you have anything that is like a spherical bowl or a spherical shell, or even something that is curved like your, I don't know, windshield, like your camera lenses, all that is slightly curved, right? So it's slightly spherical. So what happens when light falls on these spherical objects or simply curved surfaces? What will happen to the light when light falls on this particular curved surfaces? What is the relation between certain quantities like the image, form, the object, and all that? So that is what we are going to discuss in this particular session, that is refraction at curved surface. That is the phenomena of bending of light when it enters or is refracted at a curved surface. So let us take a look what happens. So here I am going to consider that there is a spherical surface or just simply a curved surface, and then I am going to say that, okay, this is the principal axis and there is an object which is considered as a point object. That is, it does not have any height, and we are considering that, okay, it is a point object and it is lying on the principal axis. Then I can say that, okay, the incident ray which is traveling from this particular object incidents on this particular curved surface, and it is then refracted. Okay, it is refracted and it is making an image at the point I. That much is clear, right? And n is nothing but the normal. So if we extrapolate the normal, it also meets at the point C, which is nothing but the center, and the distance from P to C is again the radius of curvature. All this has been discussed, you already know this, but again, this is the figure. So the consideration is very simple. In this particular figure, we are considering that O is a point object, and the angle that is made by this particular incident ray and this particular principal axis is alpha, and the angle in between the normal and the incident ray is already, you know, that is known as incidence angle or angle of incidence, that is indicated by I, and R is nothing but the refracted angle, that is the angle between the normal and the refracted ray, and finally the angle between, that is the refracted ray and this particular principal axis, is known as gamma, and the next angle, that is the normal that is making the angle here with the principal axis, is indicated as beta. So why we took different angles is because we want to establish a relation between this I and R, right? So we cannot directly do that. So the method we are adopting is a geometrical approach. So here, based on the symmetry or the shapes we have here, we can find several triangles here. So using Pythagorean theorem and those particular geometrical theories, we will find a relation between these angles, or we'll find a mathematical relation in between these. So again, we are going to start from Snell's law, which states that sine I divided by sine R is equal to N2 divided by N1. Here N1 is the material medium, generally that is air, and then the second material medium is the curved surface. So if you're using a fish bowl and a fish bowl kept on a table, then you can say that air is the first refractive index, and the N2, the second refractive index, is indicated by the curved surface, which is glass. If you're using a camera, then you can say that, okay, glass. Then if you're using it underwater, then you can say that, okay, N1 is water and N2 is glass. Like that, it actually depends. If it is a water droplet, then you can actually say that, okay, then the curved surface N2 material medium is water now. So N2 will have the refractive index of water and N1 will have the refractive index of air. For example, in rainbow formation or when it rains and all that, the raindrop assumes a spherical shape. When it falls, it is a teardrop shape, but again, it forms a spherical shape and the surrounding things are air. So like that. Generally, we can say that N1 is the first material medium, the refractive index of first material medium, and N2 is the refractive index of the second material medium. So from here, we are going to assume that the general assumptions we took already, that sine I being very, very, very small, we are going to approximate sine I to I. We already took this assumption. That is, this figure is drawn like this just for you to see, just for you to understand. In actual situation, the point object is really close. The angle made by it is really small. So hence we are saying that, okay, since sine I is very, 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 very small, it is approximately equal to I. Okay. So since sine I is very small, we approximate it to I, and we can also do the same thing for sine R, which is approximately equal to R. So since sine of the angle is very small, we approximate it to I, the angle itself, and then what we do is apply this into this particular equation. So we get I by R is equal to N2 by N1, or simply we can rewrite this as N1I is equal to N2 into R. So we have this particular result. Let's name it as equation number 1. Okay, from this figure, we have this particular angle, we have this particular relation, we are going to name it as equation number 1. N1I is equal to N2R. Now, since we have our first result, now we are going to dive into the geometrical aspects of this particular diagram. So as you can see here, we have several triangles here. So we are going to find out a relation so that from these triangles, in terms of these lengths, we actually know. So we can have a familiar equation. For that, we are going to consider the first triangle, that is ONC. Okay, we are going to consider the biggest triangle there. The second biggest triangle, and now we are going to say that, okay, from triangle ONC, we can have a relation for I. So how do we define I in terms of this particular triangle? So again, we do know for a fact that if I have a triangle like this, and here there is an exterior angle, then I can say that the exterior angle is equal to sum of the two opposite interior angles. So since that is the case, here also I can apply the same logic and say that since I is the exterior angle, then I can say that alpha plus beta will be equal to I. Sum of the interior angles will be equal to the exterior angle, that is alpha plus beta will be equal to I. So here I can say that angle I will be equal to angle alpha plus angle beta, right? So now we found a relation for I. Now we have to find a relation for R. It is very simple. So again, in order to find the relation for R, we are going to consider the next triangle, which is the smallest triangle in this particular case. So that is NCI. So considering triangle NCI, I can say that, okay, here what is the exterior angle? So here, if I consider this particular triangle, then I can say that, okay, beta is actually equal to R plus gamma, right? So beta is the exterior angle and R and gamma are the interior angles. Then I can simply say that, beta, angle beta is equal to angle gamma plus angle R. That is true, right? But what do we have to find out? We have to find a relation or an expression in terms of the refracted angle or refracted angle. So we can say that angle R is actually equal to angle beta minus angle gamma, right? If I take this gamma to the left hand side, I can say that beta minus gamma is equal to R. So I have the second relation, that is angle R is equal to, let's put it as 3, let's put this as 2. Then we can say that, okay, angle R is equal to beta minus gamma. So now what we are going to do is that we are going to substitute equation 2 and 3 in equation 1. Right. We have equation number 1 here. We are going to substitute these results into equation number 1. Then I can write N1 into alpha plus beta is equal to N2 into beta minus gamma, right? So alpha plus beta, I'm not using the angle symbols because it is understood already, that is alpha is an angle, beta is an angle. It is not magnitude values. So I'm just taking it as such, alpha, beta, and like that. So instead of I can write alpha plus beta. Instead of R, I can write beta minus gamma. So this is our new equation. And again, this alpha and beta are in terms of angles. This is not enough for us to understand or have a mathematical expression. So again, what we are going to do is that we are going to turn these angles, or we are going to express these angles in terms of lengths. Again, using the same triangular relations, we can express them in terms of lengths, which will have a more significant meaning because we know what the lengths actually mean. Because the length from the object to this particular point is the object distance. From this point P to the image, we know that it is the image distance. And the point P to C, we know that it is radius of curvature, which is nothing but R. So we do know the lengths, but we don't know what is alpha, beta, we don't know what is I, R. That is why from the exterior, we are working out a relation in terms of the interior angles and then in terms of the lengths so that we can have a mathematical expression. So that is what we are trying to achieve here. So again, the next bit is converting this alpha, beta, gamma into the known lengths that we know. So again, for that, I'm going to take or consider this particular triangle again, that is triangle ONC. So for that, I'm going to consider the triangles again, that is in this particular case, I'm going to consider triangle ONP. So, but ONP is not a triangle, that is a curved surface. Again, when we go zoom in enough, that particular curve appears to be a straight line. This figure is only there for a demonstrative purpose. So again, if I consider triangle ONP, then I can see that tan alpha is equal to opposite side, which is NP divided by adjacent side, which is nothing but OP, right? Tan alpha is equal to NP by OP. Similarly, I can do this for the other angles also, but before that, again, we are going to consider here that since tan alpha is very small, I can approximate tan alpha to alpha. So I can actually say that alpha is equal to NP by OP, right? And similarly, I'm going to consider the next triangle, that is PCN. So again, I'm going to consider the next triangle, that is PCN or NPC. So triangle NPC, from triangle NPC, I can define beta. So again, beta is equal to opposite side by adjacent side. Opposite side is nothing but NP. So tan beta is equal to opposite side, which is NP, divided by adjacent side, which is nothing but PC. And then finally, we have to define what is gamma also. So here, gamma is this particular triangle. So we are going to consider NIP or NPI. So again, from triangle NPI, before that, we are approximating tan beta to beta. So again, we can write beta is equal to NP divided by PC, right? And finally, from the triangle NPI, we can say that tan gamma is actually equal to NP divided by PI, right? Or simply approximating, we have gamma is equal to NP divided by PI. So we have an expression in terms of alpha, in terms of beta, and in terms of gamma. All we have to do is again substitute these results into this particular equation. So once we substitute these particular equations, we will get N1 instead of alpha plus beta, we are going to substitute NP by OP plus NP by PC, that is instead of alpha and instead of beta, which is again equal to N2 into NP divided by PC minus NP divided by PI, right? So we have this particular equation. And now again, when you look closely at this particular equation, we can see that the numerator will contain NP as common. So what we'll do is that we'll take the NP out as common and then we'll cancel it out. Or simply we can say that dividing throughout by NP, we'll have the relation as N1 into 1 by OP plus 1 by PC is equal to N2 into 1 by PC minus 1 by PI. So again, we do know what is OP, which is nothing but object distance. We know what is PC, which is nothing but the radius of curvature, and we know what is PI, which is nothing but image distance. The only thing you have to remember is the sign convention, that is, if it is on the left hand side, we have to give it the minus sign according to the Cartesian rule. So again, we are going to rewrite these particular equations or these particular lengths in terms of the length we actually know. So this will become N1 into 1 by minus U, minus because it is on the left hand side. OP is nothing but the object distance from O to the point P is nothing but the object distance, which is indicated by the letter U, plus 1 by PC. PC is nothing but the distance that is known as radius of curvature. If you have a spherical object, it will have a center, and that particular distance is known as radius of curvature. So 1 by PC will become 1 by R, and again which will be equal to N2 into 1 by PC is again 1 by R minus 1 by Pi. Pi is nothing but the image distance, that is the distance from the center to that particular point where the image is found. So it is nothing but the image distance, which is indicated by the letter V. So we can see that will be indicated by 1 by V. Since it is on the right hand side, we don't have to change the signs. Now, if I rearrange this particular equation, that is, if I open the brackets and rearrange that particular equation, I'll take 1 by R and 1 by R to one side. I'll take the 1 by V to one side. Then I can actually say that, okay, N1 by minus U plus N1 by R is equal to N1 by R is equal to N2 by R minus N2 by V. So I'm going to take all the terms with the R together, and I'm going to take all the terms with the V and U together. That is image and object together, the radius of curvature terms together. So then I can actually say that, okay, I'm going to take this equation to, I'm going to take this equation to the left hand side. Then I can say that, okay, N2 by V minus N1 by U is equal to N2 by R minus N1 by R, right? Or I can take N2 minus N1 common, and then I can write it as, N2 by V minus N1 by U is equal to 1 by R into N2 minus N1. So this is the final form of diffraction at a curved surface. Again, it is very easy. There is not much physical significance involved in this particular derivation. It is only a geometrical based derivation which signifies what happens when, or what happens geometrically when light incidents a curved surface. So I hope you have understood everything about what happens when light hits a curved surface, how to represent that mathematically, and what is the relation between critical angle and the refractive index of the material medium. So that is all for today's session. I'll see you all very soon with a new topic. Until then, thank you.